Hello everyone, in this video I will discuss previous year's questions of CSIR-NET exam and all the problems are from general organic chemistry. Topics will be miscellaneous. So let's start. Here we have the first problem which is saying that according to Huckel's rule, two compounds are given. We have to choose whether these are anti-aromatic or aromatic. So different combinations are given in the options 1, 2, 3 and 4. Now to understand whether a molecule will be aromatic or not, we have to keep in mind all these 4 points. So if these 4 points are fulfilled, then we can call this species as aromatic. Now to know this in detail, there is separate video on aromaticity, non-aromaticity and anti-aromaticity that you can watch. Click on the link right now appearing on the screen, top right corner. So here we have the first molecule which is cyclic obviously, and it is planar also. The second one is also cyclic and planar. Now the second point and the third point that we have to check. Now in the first case we have total 4 double bonds. That means total pi electron we can expect 4 into 2, that is 8. But there is also lone pair over nitrogen which can undergo conjugation like this. So after conjugation, the structure that we are getting, it will be these 2 double bonds still there. Now nitrogen is positively charged, double bond is here, and boron there will be negative charge over it because there is a double bond. So in this way conjugation is possible. So as this lone pair over nitrogen is also taking part in the conjugation, you have to also consider this when we will count 4n plus 2 pi electrons. So 8 electrons are coming from double bonds and 2 electron from this nitrogen lone pair. So that is why total number of electrons will be 8 plus 2, which is 10. So here conjugation throughout the ring is present, and this is also fulfilled because 10 means if you put n value 2, 4 into 2 plus 2, that is 8, 10. So that is why this will be aromatic. Now what about the next one? In the next molecule, there is also total 3 double bonds. So 6 pi electron we can see easily. But here conjugation, is it possible? See, this type of conjugation is basically possible. So after that, you are getting this double bond. I have not changed. Here we will have positive charged. This is the new double bond but negative charge over boron. So in this way here also conjugation is possible. But total number of electron is 6 pi electron. So when you put n equal to 2 in this formula, then we get we can say that this is also fulfilled. So as all the conditions are fulfilled for both the species, so both these species will be aromatic. Option 2 will be the correct option. For the radicals, 3 radicals are given: CH3 dot, CH3 CH2 dot, that is ethyl radical, and we have C6H11 dot. This is basically cyclohexane. Now the correct order for the relative rate of addition to CH2 double bond CH, then Cl. So this is like, we can write it C triple bond. Now as you can see, here if I write in the general form, the radical is like this. When it is attacking here, the double bonds will be shifted and there will be negative charge over, sorry, not negative charge, there will be radical formation over nitrogen. So in this case, if this R group, it is very electron rich, obviously this type of addition will be very favorable. Now when we consider CH3 dot, which is A, then we have CH3 CH2 dot. Here we can see only one group is attached to CH2, which is donating group. And in case of cyclohexane, this is the radical. Now from both sides here electron donation is possible. So maximum stable, that is most electron rich, not just stable, most electron rich will be C. So C will come first because more, when electron richness is very high, this type of addition will be very favorable. So C will come first, then B, then A. Option 2 is the correct option. The absolute configuration of the stereogenic centers present in the molecule 9 and 10, these two positions are already marked and different possibilities are there, RS or both S, both S, both R. So these are the possibilities. Now if I focus on the chiral center, which is 9, here we have one bond which is above the plane and 3 bonds are written like this. Sorry, this is 9 position. Now in this case, when I will consider CHO, so all the 4 sides you can see we have carbon. Now with carbon, what are the next substituents that we have to consider? So when it is CHO, the carbonyl carbon, with it there is basically 2 oxygen we have to consider as if it is attached, and then there is hydrogen because it is C double bond O. Now for downward, if you see, with this carbon, both side there is CH2 and 1 oxygen. That means there is C, C and oxygen. Now this side we have 2 hydrogen, 1 carbon, and in the left hand side we have C double bond O. That means I am talking about this carbon, it is attached to 1 carbon and 2 oxygen. So this should be like this. Now we have to mark the priority. So maximum priority, that will be for 2 oxygen 1 carbon. This we should give more priority. Then the second priority will be this one, because we have 2 oxygen 1 hydrogen. This will be the third priority and this will be the 4. Now keeping the 4 away from us, if we move from 1 to 2 to 3, so just keep your eye position somewhere here, which that means 4 is away from us. So under this condition 1 to 2 to 3, it is basically clockwise. So 9 should be R. Now same thing if we do for the 10 carbon. So I am just focusing on the 10 carbon. This is the chiral center and here we have OH. Now obviously OH, as oxygen is directly attached. Oxygen here is directly attached and these 3 sides are basically carbon. So oxygen, it will be having maximum priority, and the carbon which is present here, with this carbon we have 3 carbon present. Now what about this side and this side? When you are moving to the next carbon, this is CH2, 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 CH2. Move in the left hand side, CH2, 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 then CO. That means this side we will have more priority. But obviously after 1, this will be 2, this will be 3 and this will be 4. Now keeping 4 away from us, suppose 4 is away from us, so if you look from this side and if you move from 1 to 2 to 3, you will see it will be anti-clockwise. That means it should be S. So 9R and 10S, first option should be correct. In the gas phase, the correct order of hydride affinity for the given carbocations. So carbocations, it is electropositive species, there is electron deficiency, so it will be attracted by hydride, which is H minus. Now if the carbocation itself is very stable, obviously it will not look for hydride. So inverse relationship, the more stable the carbocation, lesser will be the hydride affinity. Now which one is more stable carbocation? Look at the first species. The first species, all the 4 conditions for aromaticity is maintained. Cyclic, throughout the ring conjugation is possible, total number of pi electrons 6, and this is planar. So as it is fulfilling all the criteria, so that is why this will be maximum stable. So maximum stable is A. The next stable is obviously B, because we have 3 donating groups, and that is why A, B and then C. So if it is a stability order, the hydride affinity order will be reverse. It will be C, then B and then A. So that is why this is the correct option. The structure that corresponds to the most stable conformation of the following compound. Here we have this compound where these 2 chlorine, 1,2 position, trans relationship, same is also for these 2 chlorine atoms. Now if you draw this molecule in cyclohexane chair form type of, that is all the 4 options that you can see, this is cyclohexane as we draw in chair form. Now in that case, when they are at 1 and 2 position and the substituents, they are trans relationship, then both the groups, it will be either EE or it will be AA. Now 2 chlorine, obviously we will prefer equatorial because that is more stable. Now if we apply that logic, any of these 2 will be correct, because in other 2 cases, B and C, one Cl is equatorial, another one is axial. That is I am talking about the 1,2 pair. These 2 chlorine on the right hand side and on the left hand side. Now B and C we can cancel, but between A and B, D, it seems as if A is more stable because it is equatorial, both the chlorine. But actually what happens here? Now to understand this, here we have a picture and I have taken it from Claydon. Page number is given, you can also check it. When this oxygen, that is with respect to oxygen, the next chlorine, if it is present in the axial position. Now what happens here, this carbon chlorine sigma star, that is the anti-bonding orbital, that is low lying, so it can accept electron density from this oxygen. Now this axial lone pair, it is correctly aligned to do that. But if you consider this carbon chlorine bond next to oxygen as equatorial, now equatorial lone pair, the black one, or axial lone pair, none of these lone pair are correctly aligned for overlap with the CCl sigma star. So that is why this equatorial bond is not preferred, this one is preferred, and answer will be the last one. The correct relationship between the following structures: identical enantiomer, diastereomers, constitutional isomers. Suppose this molecule is A and this one is B, right? Now B molecule, if I rotate it 180 degree, so B molecule I have taken, see it is same as B, this is B and 180 degree rotation. Now the new species that we are getting, suppose it is B prime. Now B prime and A, these two are basically same, right? So suppose this is A, just compare, it is same, and this is B prime. These two, if you try to superimpose, they are actually same molecule, right? So that is why these two are nothing but identical. Option A will be the correct option. The correct match for the bond dissociation energies of the CH bonds. So these bonds are basically, you have to consider in column 1 with the values in column 2. As an example, BDE, bond dissociation energy of, that is just for reference. This bond dissociation energy is given 105, so that you can compare. And this carbon hydrogen bond, this carbon is basically sp3. So as it is a bond dissociation energy that we have to consider, so always we have to consider the S character. So bond dissociation energy, that is directly proportional to S character of this CH bond. Okay. Now what about the S character of this ABCD carbon hydrogen bond? In case of D, if you see the hybridization of this carbon with which the hydrogen is added, basically you are breaking this bond. So this carbon is sp hybridized, this is sp3, this is sp2, and this is again sp3. Now obviously when it is sp, maximum energy we have to provide. That means D should be associated with maximum energy, that is D should be 3, right? And if it is so, the next hybridization sp2, where S character compared to sp3 it is high, so the next maximum energy, which is 110, that should be associated with B. So B should be associated with 1. Now D with 3, B with 1, that you can get here. Even if you only consider D is equal to 3, then also you can find it only in option D. So this should be the correct option. But how we will explain the other two molecules? So both are basically sp3, right? But in the first case, this angle is 60 degree. Now sp3, if you consider the angle 109 degree, compared to that it is very less. So the P character of the CC bond, I am talking about these two CC bond, the P character is basically here very high compared to normal sp3. Here P character is increased. That means the CH bond, which we are actually considering for bond dissociation energy, the S character of this CH bond, it is increased, because if P character is increased for the CC bond, obviously more S character will be developed in the CH bond, which is external. So that is the reason compared to the CH bond which is in C, because here angle is compared to this 60 degree it is high. So in case of C, the CH bond S character, and in case of A, the CH S character. In case of A, it is high. So the next maximum energy, we are left only with these two. So the next one, which is 4, A should be associated with 4 and C should be matching with 2, which is 71, the lowest one. So everything is matching with option D. This will be the correct option. Newman projection given below. And if you look at all the options, basically we have to choose the correct option. In all the cases, it is cis-decalin. because if we consider this junction point, these two hydrogens, any of this option if you choose, it is always cis. So it is cis decalin. And for cis decalin, when we draw the Newman projection, it is in this way. So this is a normal picture that we have written. Now this is the chair form, and from chair form, when you move to Newman, all the numbers are also given. You can compare it, how it is converted first to chair form, then from chair to Newman. Everything we can see here. But to answer this question, even we don't have to consider details of this. Even without considering that, we can solve this question. But how? Here, if you consider the junction point, especially this front carbon. So this is the carbon I am just highlighting here. Now this, with respect to this carbon, if you move this side, after one CH2 you will find Me, methyl. And if you move right hand side, after 2 CH2 you will find Me. Same thing is also for the second option. But if you consider third option and fourth option, in both side, after 1 CH2 you are getting the methyl. Now look at the molecule which is given in the question. Here after 1 CH2 you are getting this methyl, but on the other side CH2, another CH2, then in the back carbon we have methyl substituent. So C and D cannot be correct. We can cancel these two. Now we are left with A and B. But among A and B, how we will cancel one of this option? This CH3, if you see, if you consider it equatorial, then this is 1 position and this is 3 position. Now at 3 position, this is axial, but this is equatorial. And here this is axial, this is equatorial. So here we are seeing at 1 position and 3 position, we are getting equatorial. Now in these two groups, if I am marking it as 1 and if I am marking it as 3, this is 1 and 3, and we know in chair form, when in two substituents are present in 1 and 3 and they are cis to each other, both of them will be equatorial or both of them will be axial. Okay, so here in the given picture both are equatorial, so that is why we have to consider the cis one, because in this case it is trans at 1 and 3. So considering all the points, first option we will choose as a correct option. The correct relationship between the two faces of the C double bond O. So in these two molecules A and B, we have C double bond O, right? Now when we have C double bond O, just I am taking simply cyclohexane. And if you are attacking with some nucleophile, faces means what? It can attack from front face or from the face away from us, below the screen. So if the nucleophile is attacking below the screen, which will be towards us, and this is the nucleophile. Another possibility is there is another phase attack if it is happening. Now OH is below and this one is first. So in this molecule where I have started with, there is no chiral center. And after product formation, two possibilities, you are getting a chiral center and these two are related to each other as enantiomer. So when there is no chiral center and attack, that is nucleophilic type of attack we are considering, two types of products we are getting. So that is why these two phases of carbonyl, the relationship is enantiotopic phases. But suppose in this case, if we already have a substituent, it may be below the plane or above the plane, but you already have a chiral center before the nucleophile attack. So if it is so, now the product will be like this. So already there is a chiral center and you are generating a new chiral center. So obviously now we will get two diastereomer. So in this case it is diastereotopic. Now come to the actual molecule. In molecule A, we already have chiral center. Though it looks symmetrical, but actually these are chiral centers. So when there is already chiral center and you are considering whether it is enantiotopic or diastereotopic, it will be diastereotopic. But in the second molecule, there is actually no chiral center. This center is actually not chiral because both sides similar, same groups. So it is not chiral center. So it will be, that is after nucleophile attack, it will give us two enantiomers. So that is why this phase is enantiotopic. First one is diastereotopic, second one is enantiotopic. This should be the correct option. So that's all in this video. I will meet you in the next video where the questions from the next years we will discuss. Thank you for listening.